So I hope you guys see the slide 7. Can you guys see it? Is it there? Okay. So um again, so we're gonna do some review and then do some LT spice, and then we'll learn something very useful method to design in I design for MOSFET, and then we're gonna use that method for our rest of the class. So the lecture 6 was about capacitances and small signal model. So capacitances. The point here is that we have a lot of parasitic capacitances, and the characteristic of this capacitance is that they are not linear. And what it means is that their capacitance value isn't constant. It depends on the region. So I think the analog circuit is all about like setting the choose the operating point, which is a DC point, and then model its just extract this value. So what I mean is that, for example, like here, if there's capacitance looks like this, just for example, and then maybe this is maybe VGS, or whatever. Analog circuit design is all about choose this point and then just use a slope for its parameters. That's what we're going to do. That's what analog designers do. So for example, here, MOSFET, they have a gate capacitance. This is important when we think about like high-speed operation. So this capacitance value will comes again. So usually it's good to have a large MOSFET in terms of various reasons. For example, mismatch or noise. But if you have too large MOSFET, then it's slow because it's large and then it's hard to drive. So here the other example was I included this because capacitance, we can kind of reduce it by drawing differently. So there's two ways. So for example, these two in our layout, these two are the same in terms of schematic. They have same W and then same L. So here just one single channel, but here we kind of divide it, and then we have two channels, and then so overall width is double. I mean, just W, but we have a different capacitance. So I recommend you to calculate this. This is in textbook. Any question here? So gate capacitances, they calculate the various capacitance, depends on the region. This part, I recommend you to read it, but you don't have to like seriously memorize it. Just the key point here is that the capacitance value is different, depends on the operating region. That's what we should remember. So also in triode and then also in saturation, here the interesting part was, so CGS and CGD are different. So for example, here in triode, CGD and CGS here, they're the same because of the channel. Channel is like symmetry, right? Symmetric. But in saturation region, their capacitances are different. So CGS is here. Well, it says CGD. So this is CGS. And here, this is CGD. So they're different because of this channel. Channel is not symmetric. And you see that CGS is larger, right? Because they have more like this channel here. So that's the key point here. CGD is smaller than CGS in saturation region. But in actual design, we're mostly just simulated. But this is good to know. And this is also the reason, as I said, analog circuit design is kind of always find the linear value, linearly approximation. So here, for example, if you have IV curve for this MOSFET, and then let's say this is VGS. And here you see that we have a V bias here, because in this figure, you see there's V bias. So what it does actually is that, so in this, there's only AC signal is coming through because of the cap. And then we set the bias voltage here. So it's like, it's good to think as a separate thing, bias and then signal, they are different. So a bias, and then we have, this is our operating point, and then we get a GM of this slope at this point, right? And then here, what we can also think about is that what if our operating region, like VGS, changes too much? So for here, we assume that VGS, so VGS is here, right? We assume VGS, that signal range is small, so we can kind of approximate it well. But what if it is really large? Then it's a problem. Our circuit is not linear anymore. In that case, we have to consider lots of more things. For example, in real industry, one of the important factors is HD2 and HD3. That means that harmonic distortion, and that's related to also linearity. So if our signal is too large, then those linearity performance is bad. Um, any question here? Yeah. So in the small signal model, we talked about three different signals. So output conductance. So this is more like RO. This is a very important part. And then this is from channel length modulation, right? And then and here, this is VDS. What it means is that um, what is related to that symbol. I mean, the RO, that's VDS. It's about channel length modulation. And then GM, transconductance. This is VGS, right? VGS. Transconductance is related to VGS. And then GMB, body effect. This is related to GBS, the bulk to source, right? So we are modeling our small signal model of MOSFET using this. So I think let's take a look. Let's take some time to derive this equation. Yeah, can you guys just do it on your own? This equation, it's starting from ID equation. ID is 1/2 mu and series that equation. So you can try to derive it from now, because you're gonna use it a lot of time when you do analog circuit design. So we have to memorize it. Let's just take like 5 minutes, and then I'll put it in the midterm. So just try to remember. Oh, do you have your slide? Do you have question? Do you have slide? Here? Okay. Okay. Yep. So let's try the page 13. Write it down with your hand. This is very important equations. So I think time's up. So GM is, so it's just a simple calculation. And so you can just, so you know the ID equation, right? ID is, so you can just try a calculation and then the rest of it is just a simple math. But the message here is that also there was a question here. So message here is like, for example, if you see this first equation, it says if we increase, so this is VOV, this is V over drive. This is V over drive. It means that if we increase VOV with fixed mu n COX W over L, we can increase GM. But here's a question. Is ID constant if we increase VGS minus VTH? No, that will also increase. So here we said, oh, if we are increasing VGS, it means also ID is increasing. So it's like, it doesn't mean that we're only changing VGS without everything is just fixed. It's just if in the first equation, the message here is that if you increase VGS, GM will increase, but inherently, if you increase VGS, ID is increasing. But let's see the second equation. What it means is that if we, let's say, if we fix ID, we're not going to change ID, but we're going to decrease VGS minus VTH. That's the message here. That means GM will increase. So here, the message here is that if we fix ID and decrease VGS, GM will increase. Then what should we do? What do we do? What should we do if we want to keep ID and decrease VGS? We have to increase the size. So that's what it means. So here, to keep ID constant and then to decrease VGS, we have to increase W. And then the third equation here, we're gonna just fix the transistor, design factor. And then if we increase ID, then it will give us larger GM, which means we have to increase VGS. So there's a certain, that depends on the design, like limitation. Maybe in some cases, you cannot increase ID or something like that. That can happen in your design. Maybe your company or your research, we have a very limited power, so we cannot increase ID. Then what do we do? In that case, we have to decrease VOV. And in that case, we need more area. So it's kind of trade-off. But for example, here, but if our limitation is area, well, that also happens a lot in work because area is very important part. If you have a fixed area and then we want to increase GM, that means we have to increase ID, like from the third equation. So that's kind of so this equation gave us a trade-off when we designed the MOSFET. Any question here? I guess this is kind of confusing. But we'll take a look. In further in our classes because we're gonna actually design the circuit. Here GM versus VDS. So we have a equation here in triode. GM was, I just get an answer here. WL and then VDS, and then saturation GM is mu n COX WL VGS minus VTH. So it's basically like here. And then this part is VGS minus VTH. And then here is saturation, and then here is triode, which is linear region. So the message here is that to get a large GM, we have to put our MOSFET in saturation region. And then I think I'll say like almost most of the case every time our MOSFET for amplifier, they should be in saturation region, especially especially the MOSFET is in input device, then that device always have to be in saturation because that's the way that we can efficiently use our the device. Here the output resistance. Well, output resistance is from a channel length modulation, right? So if the MOSFET is ideal, we don't want our current increases or current changes depend on the VDS. But in reality, it's changing, and that's because of the channel length modulation. And then I guess one question would be, why do we need a flat profile? Why do we need that? Is because I said, and ideally what we want is flats. Because this is good because so we have in analog circuit design, what we have to do is that we have to implement a lot of current source. And then the way how we implement current source is that we use MOSFET. So this is actually just like this. I mean, we do have some cascode or something, but let's just say this is a simple just MOSFET here. So if we just assign some bias in the gate, and we don't, and then the definition of current source is that no matter how this VD is, the current should be constant. That's what we want. It means so that's exactly like here, right? So in here, VDS, even if VDS changes, the current doesn't change. That's what we want. So that's one of the reasons why we want a channel length modulation really small. Does it make sense? Any question here? I think this can be confusing. So the point here is that we don't want channel length modulation. We want our MOSFET to be ideal. And then one of the reasons for that is that when we design current source, that ideal MOSFET give us a perfect current source. But if we have channel length modulation, which means if we change VDS, current changes, that's the channel length modulation, right? If that's the case, we cannot make a good current source. So that's one thing. And the other thing would be when we design the amplifier to get a large gain, I think that's the next common source lecture. We want a large like output impedance to get a large gain. So again, if we don't have channel length modulation, that's good because we can have a really high gain amplifier. We're gonna get there. But anyway, the point here is that we don't want it, but that's the reality. And then we have to model it. Body effect transconductance. I honestly didn't use it much in real design, but no, maybe I should. Maybe I did. But the point here is that because of the body voltage, like here, let's say if you have an NMOS, and then let's say there is a resistor, then here VB is 0 and then S. S is not 0, right? So in this case, our VTA changes. And then that changes the like GM or GMB. And then some circuit also kind of utilize this that part by changing the source bulk voltage or source voltage. But anyway, the point here is that because of the VBS, the threshold voltage changes, and then it turns out to be like a here GM like impact. So here's the small signal model. Well, this is very important, of course. We have to memorize it. We always use it for our circuit analysis. And then here you see that this is just disappeared, right? Because VBS is 0 because they are just connected in NMOS. And then usually this is ground. Well, I mean, these CSV, this CDB, we usually not looking at it in reality, I mean, in real design, but I think it's just good to know that there's a bunch of capacitance here. And then this also I put it here because there is a gate resistance. What it says is here, there's a layout. But I wonder, does anyone do a layout before? Anyone has experience? Okay, you, and then okay, then okay, you. Then it may not be familiar to you. So again, as a circuit designer, what we do is that we design the circuit first, and then like the way how we design circuit is like this, just this kind of MOSFET schematic. So we said it's schematic design, and after schematic design, what we do is that we actually draw this kind of thing. So we actually draw in layout, like using this, something like this. Well, MOSFET is usually they already give us a pre-designed value. I mean, pre-designed so we call it as a P cell. So they give us pre-designed MOSFET, and then what we do is that in layout we just put some W, or how many fingers do you want, and how large the length is, something like that. But we still have a choice. Like for example, here they're different because they use different finger. So this finger is one, this is finger one, and this is finger two. So that's what we have to choose. And then depends on this finger, we have a different performance of circuit. So drawing layout is also very important important part of the analog circuit design. So here, what they said is that, so you see here, this is where we apply like a voltage source, not a voltage source, but like just, let's say, input here, right? Then you see here, this part is kind of far from there, right? You see this part? So this part is far from our source, so which is bad. It's slow. But this one in our second, this is better because we can apply a voltage faster. So again, the point here is that depends on how you draw the layout. We got a different circuit performance, and then it's really important to draw a good layout. And I just put FinFETs. That was in, so these are like kind of hot. I mean, very popular. So it's good because it has a more like, so FinFET is like less than 20 nano. That's what the book says. Well, actually, I've never used FinFET in my design, but so in FinFET, let's say very advanced technology, the gate and source are no longer 2D. It's like 3D, right? So just a normal MOSFET looks like this. Just a normal MOSFET looks like this, but this one, so in normal MOSFET, they only have this part to control, but in here they have more like surface, so it has more controllability. It has more good current controllability. So it's very good, but I think in 3 nano, from 3 nano, they cannot use FinFET anymore because they are back to the normal MOSFET because of the so for my experience, what I did was I did 28 nano design that didn't use FinFET, and then I did 3 and 2 nano design that also didn't use FinFET. I never done the between technology, so I have no experience on that. But what I heard is it's really, so in terms of layout, it's getting, I would say, hard and easy, because if the technology getting advanced, it gives us a lot of constraints. it just doesn't give us freedom to draw. That's good in term and something like we don't have any choice, so there's nothing to think about. But also it's hard because we have to, I mean, because we have a lot of limitation. We have to get a good circuit design from that. So, okay, let's go to the LT Spice again. I think let's turn LT Spice. So today one is important. Well, this is not only about LT Spice. It's just about like general analog circuit design. So let's try page 22. And then I see 12 people submitted assignment, but we are 13. I guess one guy didn't submit it. Wow. 아, 고마워요, 알려줘서. 다 냈네. So we are 100% submitted. I try to be generous. So let's try to do this. Again, so I always acknowledge my friend, Seung-jong Lee. So I also learned from him a lot. And so this is like his like go-to method. So I think it's really good to learn. I think this method is like very intuitive, and then it gave us the good starting point of the design. I think one of the hard part of the analog design is that where should we start? I mean, that's the hard part. But it gave us a good intuition. So once you do that, you can just keep going. So in color is so dark. And try page 23. So here, our last assignment was at guess VTH, right? Just guess by your eyes. But here we're gonna use some equation and then get VTH. 그게 제가 이제 회사에 있을 때 애플에 있을 때 위에서 우선 이게 3나노 정도를 어떻게 되냐면 실습 시설 때 이 3나노 이제 나온 차에 우리가 쓰는 뼈로 그냥 이렇게 같은 거 한번 해봐요. 그리고 서로 이제 모델링 같이 하거든요. 근데 이제 어려워요. 디자인 네. 그때만 이제 비교하는 표 같은 게 있었는데 아날로그는 내려갈 수 있는데 아, 이거 끝나. 아, 그래. 그런 식으로. 그 이강 하나 만들어. 네. 각 20나무가 28나무까지 되게 성능이 올라가면 맞아. 이거 떨어지죠. 맞아, 맞아. 근데 이 떨어지는 여기서 어쨌든 여기 들어오는 이거에 대한 보상으로 이걸 사이드 키우면 이게 보상이 돼요. 네. 그래서 이런 것들을 혹시 이렇게 그래서 저도 그렇게까지 자세히 있는 거 알아봤고, 뭔가 막 제품형으로 해본 건 아니고, 그 예를 들어서 막그 모뎀치 있잖아. 이런 거는 그냥 그거 안 써요. 이런 애들은 인식하라고 써요. 그러니까 제 생각에는 막 M3 이런 완전 디지털화된 기술이잖아. 아니면 걔네들은 안 하고 파탄 따르니까 아무 천에가 봐도 인플을 받는 그 보니까 그런 거고 그렇다고 이제 막 모뎀치 이런 아날로그 중심 기술을 안 써요. 그대로 28나노스 그거를 나눠서 LTCC나 이런 데 직접해서 그런 건데 그렇게 할 것 같아요. 칩이 다 공정이 다 나온다고. 이제 뭐 M3 이런 애도 아날로그가 필요하니까 그러면 예를 들어 칩이 레이어 1, 레이어 2가 네네. 12가 될 수도 있고, 네. 그럼 이 부분 어떻게 해요? 그 사이요? 사이 커넥션? 뭐 글쎄요, 저는 거기 안 해봤지만, 뭐 아마 좀 되게 높은 레벨에서 되기는 하니까, 트랜지스터 레벨까지 되기는 하나. 예를 들어 서로 되게, 이거 신호 사이 왔다 갔다 하는 거 그런 거. 뭐 그러면은, 신호 모델, 드라이브 모델링 하는 거, 튜브레이스나 얼마큼 수가 있는 그런 거 아니면 그러니까 이게 아내가 뭘 쓰던 간에 뒤에 서로 통신하는 애들 모델링을 신호를 원하는 대로 나오는 거죠. 받아들이는 그러니까 내부 사정은 또 그쵸 저도 이해요. 저도 이 수도 어떻게 하면 되겠어요. 그냥 하고 할수 있어요. 계속 네, 계속 한번 해보세요. 아까 저쪽 질문 있지 않았나? 아, 계속 보이는 건데, 이거 일반 경우 네, 헷갈려. I'm sorry. Can you just take a look? Can you look at here? So the reason why we use this square root is that what's our current equation? That's right. So we're just square root ID to get there's let's say just K and then VGS minus VTH, right? And then by using the linear equation, we can get this VTH. So um, let's go to the page 24. You guys can do it and then let me know if you have questions here. So and then I recommend you to make this kind of Excel file to calculate things. You will see what I mean if you go through the slides. So I guess a lot of students may wonder how in this slide, how do they have like exact 580 or exact 660? So I couldn't find how to put number in it, but what we can do is that click the cursor and then use your like arrow button in your keyboard. So assuming keep doing what you're doing, and then so in 24, what we got is so purpose is that we want to get this VTH by using this, and then also this mu and COX, the value. That's our purpose here. And then once we got it, we can design NMOS. So for example, when we design NMOS in analog circuit, the requirement is like, oh, we're gonna use this amount of current, and then well, GM also we sometimes we want GM, but also sometimes we want like V overdrive because overdrive is related to the voltage headroom. So either ID or GM or VOV, that's given in our purpose. Once we got that condition, then we can design MOSFET by using this method. So again, our goal is with a given, for example, here, given current and then given GM, because in our circuit, these are our target. We can find the MOSFET size. That's our purpose. So just keep going. And once you're done, we can also do PMOS design with this. There is some tricky part with PMOS. But you can ask me once you're there.